So what's still pressing on the bruise? For a long time, scientists treated the ozone narrative as top-down. Industries emit, chemistry reacts, policies pull us back. But the Earth doesn't run on simple stories, it cycles. Old seafloors slide under continents and then millennia later reappear as magma. The Afar region in East Africa is a case in point. The Mantle plume beneath it has a helium isotope signature that hints at deep sources, yet oddly low helium concentrations. Evidence of recycled oceanic crusts mixed into its melt. Subducted slabs are loaded with salts and halogens. Heat and melting can liberate those halogens. Meanwhile, hotspots like Hawaii, Iceland, and the Galapagos tap reservoirs that carry primordial signals. At the Galapagos platform, basalt glasses carry helium ratios that shout undegassed mantle. Helium doesn't destroy ozone, but it's a tracer that tells you where your plumbing runs. Follow those pipes and you find something else hitchhiking. Volcanic halogens. Hydrogen chloride and hydrogen fluoride, yes, but also bromine species that pack an outsized punch. Most of those gases dissolve in eruption clouds and rain out quickly. Still, under the right conditions, especially in the tropics, very short-lived halogen compounds can ride convective towers into the lower stratosphere. Add one more twist. The same circulation that ferries air poleward has been changing. When the conveyor speeds up, it can loft those short-lived gases higher and faster. And when a volcano seeds the stratosphere with sulfate aerosols, it builds chemical playgrounds. Surfaces where halogen reactions accelerate. That's why some eruptions punch above their weight for ozone. Not because they inject chlorine as high as Pinatubo did, but because they rewire the chemistry for a season. All this complexity sets up the puzzle we face now. We close the tap on man-made CFCs, yet natural taps open and close with the planet's own heartbeat. During certain years, bromine and iodine from ocean biology surge into the lower stratosphere. During others, tropical updrafts carry a little extra. And from below, the deep earth keeps exhaling. Not in a constant hiss, but in pulses we often notice only after the ozone data bend. None of this erases the Montreal Protocol's success. Without it, the hole would have widened, and UVB would be carving through mid-latitudes daily. Instead, we have a recovery trend with noise. Noise that matters if you live under the southern sky or you work outdoors. That's the fragile shield we nearly lost, patched but still scuffed. It's robust enough to save countless lives, but sensitive enough that a plume from an Icelandic volcano or a shift in tropical winds can bruise it for a season. Meanwhile, down in the mantle, more is brewing. The helium signatures tell us the plumbing is active. The subducted slabs tell us the chemistry is stocked. The question waiting ahead is simple to ask and hard to answer. How much of that deep Earth leak reaches the ozone layer, and when does it matter? The mystery signal in the sky. The first hint wasn't dramatic. It was a skew in a ratio only a handful of labs watch. At a field station on Djibouti's coast, a researcher lifted a tiny chip of basalt glass from a dredge hull along the Gulf of Tadjoura. Later, in a noble gas lab, the reading came back odd. Helium-3 to helium-4 higher than the upper mantle signature, but paired with overall helium concentrations lower than expected. It didn't fit the old picture of a pristine, volatile-rich deep source. It looked mixed, deep mantle flavors cut with something processed and volatile poor, like subducted oceanic crust starved of helium. Meanwhile, satellite spectrometers tracking the southern sky were logging a different anomaly. In years when the ozone hole should have been modest, the lower stratosphere over the South Atlantic and southern Indian Ocean showed extra catalytic activity. Short-lived halogen fingerprints that didn't track with any industrial inventory. Not a spike, a patient pulse. Ground instruments in Patagonia and South Africa saw the same chemistry nudging UV indices up a notch during shoulder seasons. It wasn't enough to ring alarm bells, but it didn't go away. The Afar plume offered a clue about the source plumbing. Along the Red Sea Ridge, helium ratios rose toward values seen in high-flux plumes, yet the mantle end member there held surprisingly little helium. The best fit wasn't a single reservoir. It was a cocktail. Young recycled slab material, depleted in helium from its time on the seafloor and passage through subduction, blended with a deep, high 3He component. If that slab carried halogens, as oceanic crust does, heating at the mantle transition zone could liberate them into melts that later emerged along rifts and ridges. Then the atmosphere chimed in, Aircraft campaigns sampling the tropical tropopause picked up very short-lived brominated compounds in amounts large enough to matter. Most came from the ocean, yes, but in some profiles the vertical distribution hinted at additional sources and pathways. During strong convective seasons, those compounds slipped past the atmospheric scrubbing layer and seeded the lower stratosphere with bromine that works in tandem with chlorine on sulfate aerosol surfaces. After certain modest eruptions, the chemistry brightened. The sulfate haze built more reaction sites, and ozone dipped more than models without those halogens predicted. A pattern started to form across disciplines. In geochemistry labs, tiny melt inclusions in volcanic crystals preserved halogen ratios different from shallow crustal contamination. In seismology, tomographic images beneath East Africa and the Western Indian Ocean trace sluggish zones rising from the transition zone, the likely mixing chamber where slab fragments and hotter mantle interact. In climate models, when researchers dialed back man-made ozone-depleting substances per the Montreal Protocol, but allowed natural halogens and transient sulfate aerosols to fluctuate, the simulated recovery still held, just with lumps, especially in the southern hemisphere summers that ozone holes disturb. One winter, a brief paper caused a stir in a small circle. A team comparing helium and trace element systematics along the Red Sea argued the UFR Plumes helium concentration was only a fraction of the ambient upper mantles. The paradox sharpened. High 3 He 4 He without high helium implied most of the mass flux wasn't deep helium-rich mantle. It was slab-derived material, likely rich in incompatible elements, including halogens. If that's what fed rifting magmas reaching the seafloor, then some portion of the Earth's exhalations isn't just CO2 and water. It's halogen-bearing species that can be transformed in the atmosphere. The mystery signal in the sky, the stubborn seasonal halogen chemistry, and the mixed mantle signature underground began to look like two halves of the same loop. Subducted crust descends, loaded with chloride, bromide, and water. At the transition zone, slab edges warm and weaken, stirring with hotter mantle to form plumes with distinctive helium fingerprints and chemical cargo. Magmas ascend through rifts like a far, or leak under ridges into the oceans. At the surface and in shallow seas, those gases partition. Some dissolve, some react, some form organic halogen compounds. Under strong tropical convection, and with the Brewer-Dobson circulation quietly sped up, a fraction gets lofted into the lower stratosphere. Add a veil of sulfate from a distant eruption, and suddenly the stage is set for a sharper ozone bruise than the CFC curve alone would predict. This wasn't a catastrophe hiding in plain sight. It was a feedback we hadn't budgeted for. Policies fixed the largest lever, industrial halocarbons, but the planet's internal conveyor still cycles halogens from seafloor to sky. In years when slab-source plumes are active, when tropical oceans are churning out more very short-lived bromine, and when the stratosphere is seeded with fresh aerosol, the chemistry can lean the wrong way for a season or two. The ozone layer keeps trending toward recovery, but the line isn't smooth. In the data, the signal is modest, measurable, consequential, but nuanced. On the ground, it translates to a few extra days each spring, when UV levels spike higher than anyone expected in the 199s. For a farmer near Nuquin, that's leaf scorch on a sensitive crop. For a kid in Cape Town, that's a sunburn faster than last year's. For the scientists comparing notes, geochemists with helium ratios, atmospheric chemists with bromine columns, dynamicists with circulation trends, it's a new chapter. The Earth's core isn't leaking doom, but the deep engine is feeding a chemical loop that reaches the sky, and every few years we can watch it write its signature across the stratosphere. Into the deep, hidden oceans, and ancient salts. To see how deep Earth feeds the sky, we have to dive where water and salt stop being simple words. Beneath our feet, between 410 and 660 kilometers down, sits the Mantle transition zone, a pressure-cooked pantry stuffed with minerals that can hide entire oceans worth of water. Not liquid water in caverns, but hydrogen locked into crystal lattices of wadslite and ringwoodite. Those same minerals can host halogens, chlorine, fluorine, in trace amounts that add up when the reservoir is planet-sized. Subduction sends them there. Old seafloor crust and sediment salted by eons of seawater gets dragged under, dehydrated in stages, and salted again by metamorphic reactions that move chlorine into denser phases. Over millions of years, that cargo doesn't vanish, it waits. The waiting ends at edges and corners. Slabs don't always plunge straight to the core. Many stall in the transition zone, fold, and fray. Their edges heat first. That's where mixing starts. Cool, halogen-laden slab fragments rubbing up against warmer mantle rising from below. Seismic images beneath East Africa draw this in broad strokes. Slow anomalies rising from the transition zone toward afar, a likely mixing chamber where slab material and hotter rock concoct melts with unusual chemistry. That chemistry is the quiet thread linking a chip of glass dredged from the Red Sea to a subtle shift in ultraviolet over the Southern Ocean months later. Ancient salts hitch a careful ride. Chloride and bromide, originally bound in oceanic crusts, migrate into denser minerals as pressure mounts. Some halogens move with fluids released during subduction and escape into volcanic arcs, but a fraction is retained deep, trapped until heat and partial melting free them again. When that melting happens near the transition zone, the resulting magmas inherit a fingerprint, halogen ratios that don't match shallow contamination, trace element patterns that point to recycled slab, and, crucially for our story, helium signals that say the source isn't just the upper mantle. In afar and along the southern Red Sea, that fingerprint shows up as moderately high 3He paired with surprisingly low absolute helium. It argues for a plume dominated by helium-starved slab material spiked with a dash of deeper high 3Hack flavor. Those magmas don't need to roar skyward in spectacular eruptions to matter. Much of Earth's degassing is the slow breath of ridges and rifts. Along young oceanic crust, melts percolate, cool and exhale volatiles into seawater and the air just above it. Hydrogen chloride, hydrogen fluoride, and minor bromine-bearing species dissolve readily, but not all at once and not in the same place. In warm tropical waters under vigorous convection, some halogen chemistry shifts toward very short-lived organic compounds, bromoform dibromomethane, that resist immediate scrubbing. Those can be lofted if the timing aligns to the lower stratosphere where they count. Meanwhile, deep water plays a second role as saboteur and enabler. Water lowers the melting point of mantle rocks. Where subducted slabs hydrate the transition zone, melts can form more easily, tapping those hidden reservoirs and mobilizing the salts within them. That's why the ocean in the mantle isn't just a curiosity, it's a lever. It sets the stage for when and where ancient seawater chemistry returns to the surface, packaged in magmas, fumaroles, and invisible exhalations under the sea. This is where a geochemist's ledger meets an atmospheric chemist's calendar. The ledger lists sources: recycled crust delivering chloride and bromide to deep storage, transition zone melts releasing halogens into rifts like afar and along ridges, hotspots tapping deeper domains marked by high 3He signals. The calendar tracks doors, the tropical tropopause when convection peaks, seasons after small eruptions seed sulfate surfaces, months when the Brewer-Dobson conveyor runs a little quicker in a warming world. On their own, each box looks tame. Together, they line up just often enough to bruise the sky. There's a human picture inside the rocks. Millions of years ago, salt settled on ancient sea floors. Those beds slid under continents, were pressed into new minerals and stored in a dim mantle pantry. Heat and mixing turned some back into melt. That melt crept toward rifts that today split farmland and villages in Ethiopia. Gases seeped out, mostly water and carbon dioxide, but laced with halogens. Some dissolved in the Red Sea. Some reacted in the tropical boundary layer to form fleeting brominated compounds. In a week when storms towered higher than usual, a slim fraction slipped past the atmospheric scrubber. Come summer over the southern hemisphere, a veil of sulfate from a different eruption thousands of kilometers away made the lower stratosphere a more efficient workshop for halogen reactions. The ozone numbers dipped. A kid wore a hat and still got pink faster than last year. None of this points to a single villain. It's a loop. Salts from ancient oceans ride down and, much later, ride up as gases. The mantle's hidden water makes that ride smoother. The atmosphere's shifting winds and chemistry determine whether those riders step into the stratosphere. And in between are instruments. Mass spectrometers parsing helium in basalt glass. Satellites watching ozone's seasonal pulse catch the loop in motion. It's less a leak than a breath. Slow, deep, and connected to the sky in ways we're just starting to map. The leaky plumbing, mantle plumes, and volatile highways. If you want to know how the deep Earth breathes, you don't start with ash clouds, you start with ratios. Helium in basalt glass is like a dye in the water, high 3. He, 4. He tells you the flow taps a less degassed, older reservoir. Low absolute helium can mean the pipe is full of recycled crust that lost its helium long ago. The UFR plume sends that mixed message. Along the Red Sea and Gulf of Tadjoura, helium ratios climb toward classic plume values, while the actual helium concentration stays lean. The simplest story is mixing. Slabs rich in salts but poor in helium blending, with a pinch of deep, high 3. Mantle. Now pair that plumbing with geography. Plumes don't just rise anywhere, they favor weak spots. Rifts, ridges, thin crust. UFR is a triple junction, a natural vent. So are volcanic islands parked over hotspots and the youthfully spreading Red Sea. Those are volatile highways. The traffic isn't only carbon dioxide and water. It's halogen-bearing species that, depending on pressure, temperature, and melt pathways, leave the mantle as hydrogen halides, metal halides, or precursors to short-lived organics once they reach the surface ocean. Most days, the highway feels quiet because scrubbing is ruthless. Hydrogen chloride and hydrogen fluoride dissolve in minutes to hours, but the roadway widens in the tropics, where deep convection punches through the tropospheric ceiling. They're very short-lived brominated compounds, some human, many natural, and a portion born where magmatic halogens meet biology, can catch an express ride to the lower stratosphere. It's not a flood, it's a steady trickle that matters, because bromine is efficient. Molecule for molecule, it hits harder than chlorine, and it teams up on sulfate aerosol surfaces to accelerate ozone loss. Here's where the leaky plumbing shows its timing. The Brewer-Dobson circulation is the conveyor moving packages from the tropics to the poles. In the late 20th century, it sped up. With ozone recovery underway, models show it easing, but not equally everywhere, every season. In Southern Hemisphere summer, the season the ozone hole already tips the board. Small boost in upwelling and transport can carry more short-lived halogens higher, sooner. After a modest eruption seeds sulfate into the lower stratosphere, the reaction network gets more efficient. Precisely where the conveyor delivers the goods. Do plumes themselves blast halogens into the stratosphere? Rarely. The Pinatubo-style injection is the exception, not the rule. Most of the deep Earth's contribution comes as background degassing and submarine leakage along ridges and rifts, the unglamorous breath that goes on regardless of headlines. That's why helium is such a useful tracer. At the Galapagos platform, submarine basalt glasses record 3, He, up to 23 times the air ratio, a clear signature of a relatively undegassed plume. You won't smell helium. But if the plumbing links that plume to the surface, other volatiles are riding along. The UFR data sharpen the picture. A plume with high 3 He but low helium concentration means slab-derived mass dominates the melt. What do slabs carry? Chloride, bromide, and water bound into minerals that survive deep burial. Seismic images place Tethyan slab fragments stalled in the Mantle transition zone beneath East Africa. That's a mixing basin. Heat the slab edges to ambient mantle temperatures, add a dash of hotter mantle from below, and you've got melts that liberate deep-stored halogens without needing a supervolcano to announce them. Follow those melts north along the Red Sea, and you hit new oceanic crust forming today. Most degassing happens underwater. That's a problem and a clue. In warm tropical basins, halogens entering the ocean can be transformed into organic carriers, bromoform, dibromomethane, that live just long enough to reach convective tops. Satellite and aircraft profiles over the tropical tropopause pick up those compounds where models need them most. They're not all from reefs and algae. Flux inventories suggest a non-trivial slice is consistent with geological sources modulated by ocean chemistry. Meanwhile, the atmosphere provides the amplifiers. Sulfate aerosols from eruptions, even moderate ones, build the reaction surfaces that halogen radicals use. Cooling in the lower stratosphere from aerosol veils shifts rates again. Stack that on a circulation that shuttles air poleward faster some years, and you get seasonal dents in ozone recovery where the chemistry is primed, especially over the south. None of this works if the deep pipes are sealed. They aren't. Diamonds bring up inclusions with halogen signatures from depth. Transition zone minerals like ringwoodite can host water and trace halogens, proving the pantry is stocked. Helium anomalies flag the active taps. Put the map together and you get a network. Slab to transition zone storage. Plume upwellings that mix and melt, rifts and ridges that vent, tropical oceans that process, and atmospheric highways that deliver the last mile. Is it controllable? Not in the way CFCs were. It's geological. But it's predictable enough to matter. When plumes are active under tropical seas, when convective seasons are strong, and when sulfate is fresh aloft, the plumbing leaks more effectively into the sky. That's when the bruise shows.